Hey guys, it's Mr. Sheeline here. This is going to be the video lecture notes concerning the Unit 6.1 notes covering waves. Okay, so let's just go ahead and just get going. Let's get started here. So here are the student learning objectives. So what I want you guys to be able to do is just define a wave and the properties of a wave by the end of this. Explain what determines the frequency and velocity of a wave, and to solve basic wave problems. Okay, jumping straight to it. So waves are everywhere in nature because waves are just a way for us to not for just us, but just it's a wave transferring energy. So we see waves in the form of sound waves, light waves, radio waves, microwaves. So even when you heat up your food, you're using energy in wave form to heat up the water, which then heats up water molecules, which then heats up the surrounding food within the microwave. There's sine waves, which all sine waves are, just super quick. All sine waves are like these guys, so they're the ones like, oh, if my pen would work, my goodness. So they're like these guys. Okay, and imagine that they are moving in this direction. They just continually like around the same size. They're just kind of moving across the screen. Those are sine waves. And we can hear them in stadiums, or see them in stadiums. So when people do the wave, like at a football game, a soccer game, they do the wave. Same difference. It's like pretty much how waves work. And we'll get to that when we kind of talk a little bit about surface waves. I guess later on in the just whole unit. Earthquakes. Earthquakes emit energy in the form of waves across the land. Waves on a string, which we'll work on in this unit. And especially we'll see that specifically in slinkies, etc., etc. Okay. So what is a wave? Well, a wave is just a disturbance that travels through space, transferring energy. Okay. So waves transfer energy. They don't transfer matter, which is going to be a tough thing to kind of grasp, because especially talking about surface waves, more or less, and what surface waves are, what we see like in the ocean by beaches. Water does not move. I know that seems strange, but the water is not the thing that's moving. The matter's not moving, okay, or at least it's being carried. The energy is being carried. The water stays, roughly speaking, about exactly where it was sitting. And again, we'll get a little bit into that when we get further into the unit. So a wave, again, just a disturbance, transferring energy. Now, medium is going to be important. So what a medium is in this case is the substance or material that transports or carries the wave from its source to another location. So it's not the wave itself, it's what carries the wave. So if we were making waves in a slinky, the slinky is specifically the medium. When we see waves in the water, the medium is the water, okay? Because again, a wave is not the thing that's being moved here. It's the energy. It's the measurement of the energy moving through the thing, like water or a slinky, or even a string or a rope. And then we have this word equilibrium that we've probably seen before, and it's pretty much the same thing here. It's just the natural or rest position of the medium. And arguably it's just equilibrium is just the rest position, the equal balance of forces on an object to make it not move more, or to continually move it at a constant velocity in a uniform motion. Anyway, that's the natural or rest position of a medium. So all types of traveling waves transport energy. That's specifically what they transfer, not matter. Okay, it does not transfer matter. So again, I know that seems odd. I know that seems weird, but waves transfer energy, not matter. So a study of a single wave pulse over here in these pictures shows that it begun with a vibration. So meaning it begun with picking up the string and then transmitted through internal forces in the medium. So we pick it up, we throw it back down, and then we see this picture right here. And then what we see here is that the energy that was first put together by raising the hand then transfers through our medium, our string, okay, and it more or less travels through it. okay, making it bend its shape a little bit when it goes through, okay? And we've seen this before. We've probably done this before with strings or with ropes or whatever, hoses, okay? Now, when we make these waves, though, we can make them. When we make these waves or we see waves, generally they're in two forms. Either they're transverse waves, so these kinds of waves make and force the medium to vibrate perpendicularly to the wave's motion. So, looking at this picture here, and what I'm doing, I'm drawing what we'll get into in a bit here. This is called the equilibrium point. So what we have here is actually, we'll just get rid of that. So what we have here, it says here, the medium vibrates perpendicular to the wave's motion. So now we've got these arrows here, and I'm sure you're like, well, isn't that the way it's moving? No. So I know we've got a hand over here. We do have a hand over here, but let's just kind of let's get rid of that hand. Let's say this hand doesn't exist for a bit here. Okay, let's say that hand doesn't exist. Okay, can you increase the? No, I can't. So the direction that the waves are moving we'll say is in this direction. The waves are going to move in this direction here. Okay, so that means that when we see these, that means like this is what we would see if like continually over and over and over again, and they'd be moving in this direction. But the thing is that the waves they're moving in that direction, but they're vibrating, or they are what we could say oscillating up and down. Hence why we've got like this upper portion and we've got this lower portion of a wave, this squiggly line, okay? And what we call here, we call them transverse because they move in multiple directions. They move in multiple directions, and against more or less, you could say, are in an opposite direction, or I should say, no, it's just a perpendicular direction to its motion. Because again, the motion's in this direction, but it vibrates up and down. Okay, and we can see that if we forget which one's which, we can think of it like this. When we write out transverse, when we write the T out, we could think like, oh, well, a T written like this. Okay. Written like that, the T, we've got arrows moving up, we've got arrows moving this way and this way. We've got multiple directions of motion, transverse. And we compare that we'll compare that with and against longitudinal waves, which this is where we have waves that vibrate parallel to the wave's motion, okay? So, and if we, again, just real quick, look at this. So the transverse, again, moves perpendicular, so it moves up and down and side to side. Longitudinal basically just moves, let's say, side to side. If the motion's side to side, the vibration also moves side to side. It's one direction. And we see that here with the slinky. And we have these little areas here that we'll get into further as we go along, and especially when we get the sound waves, we'll look at this a bit more closely. But we do need to know or see that these are a thing now. But they've got these two areas. They've got this area that's called rarefaction, and they've got this spot called compression. So rarefaction, real quick, and I'd make a note of this, is basically where we have the separation, or this, like we're having it's the area where the energy is either not there, or it is, how would you say? It's a position that does not have the energy. It's a position where it's less, the medium is less dense. So we'll just say that. So we'll say medium less dense. So rarefaction, you can think of it as just, it's spreading out. It's being stretched out. Where compression is just the opposite. Compression is medium is denser. This is where your medium comes together. It's where you have more energy packed in this wave form. Okay, and again, we won't get into too much specifics, but you do need to recognize and you need to know that position, this particular part of a wave, especially again when we get to sound waves. So anyway, So the waves are going to be moving in this direction, and so are the vibrations. As we see here, the compressions are going to move this way, and the rarefactions are going to move this way as well, parallel to the motion. Okay, so that's the difference between longitudinal and transverse. So I'm not going to go over the check your understandings here. That's going to be in the separate video. So after we're done with the notes here, make sure that you go and find that video. If just a reminder though, remember I do want you to complete those all these check your understandings, and then after you've completed the check your understandings, double check your work and double check what you've done. By then going to the check your understandings videos and doing that. Okay, parts of a wave. Here I've got these labeled out. We're going to draw these on the actual slide here. So on the next slide. So parts of a wave, we have what's called amplitude, crest, trough, and then just the wavelength. So the amplitude is the maximum distance the wave moves away from its equilibrium position. We'll get to where that guy is in a bit. Then you have the crest. This is the highest point on a wave. Trough, the lowest point on a wave. Okay, and then we have wavelength. This is the distance between two consecutive crests or troughs. So let's kind of point this out here on here. Okay, so again, and I've got to first point this out, but the equilibrium point. So we see the equilibrium point, and I'm actually going to make this green. I'm going to make the equilibrium point green. So the equilibrium point is this straight line right here. Okay, now the reason why we want to keep track of what the equilibrium point is, again, because this is the resting position of our medium. So if this is a rope, that's what the rope would be, while it's just sitting there before we put any energy in it. Okay, so that's the equilibrium point. That's what it used to be. So talking about that, here's where the amplitude is. So here is the amplitude. Okay, the amplitude is the distance from here to here. Okay, it's also this one right here because it's the distance from the equilibrium point to the crest or the trough. Excuse the bell. Okay. And then we have the other one we have here is the crest. And the crest is going to be the highest point of a wave. So here's the crest. And then the lowest point of a wave is going to be down here. This is the trough. Okay, that's a trough. So crest, just like the crest of a mountain. Okay, the tippy top point of a mountain. Trough is going to be like an animal trough. It's the thing that, for like, say, cows, we'll say. It's what you put the seed in, the grain in, and the feed for the cow. It's where a trough is what you put water. You put water in a trough for cows or horses, for them to drink out of. So it's this. We see that. Hopefully, we see that. Okay. So, no, eraser. So there's the crest, there's the trough, there's the amplitude. Now, where's the wavelength? So remember, wavelength is basically from crest to crest or trough to trough. So it'd be like this position to this position right here. That distance between here and here, this is the wavelength. Okay, that's the wavelength. Okay. Or it could be from here to here. This right here is the wavelength. Okay. So that's pretty much easy peasy, just writing out what the parts of a wave are. Okay. Now, here's how we're going to label some of these things. And I know I'm throwing frequency and velocity in here last second, and I'll explain those in a bit. But wavelength, because we're going to be measuring what the wavelength is, again, which is the length of a single complete wave, we categorize wavelength with the variable or with the symbol. Like this really should say symbol. Okay. These are the variables over here, arguably. or at least the way I talk about them, those are the variables. Okay. The symbol here is going to be this weird thing. This right here is lambda. Okay. Actually, I don't remember if there is that B in there, but it's lambda. Something to look up, actually. Okay, it does have a B. I just quick looked it up. Okay. Excuse me. So lambda here, this symbol right here, indicates, or we use that, to show for wavelength. And we measure wavelength in meters. Okay. So it is, again, to reiterate, wavelength is this. Wavelength is the distance between here and here. Okay. Now, there was a couple other things in there. There was frequency, the thing called frequency, and a thing called velocity. So, but those are no different from what we have looked at before. Okay. Oops, stop it. So frequency is just the number of cycles per second. It's a number of things happening per second. Velocity is just how quickly the velocity of the wave is moving. So again, number of waves per second for frequency. I'll go back, and I'll finish up talking about that. So that frequency, we use remember, symbol. We use the symbol F, and we measure it in units of hertz, which hertz, now we'll be focusing more about how, like, hertz is usually how many times a wave oscillates, how many times it moves past the number of waves. Oh my goodness, it's how many times that they oscillate. So how many waves do we see for every 1 second? That's what frequency is. Okay, that's what frequency is. Now, velocity of a wave is, again, just how quickly a particular wavelength moves across the screen, or just across the medium. And I'll show you here in the next slide. So if we've got our wavelength here, here's in lambda. So it's like if we were to do this, if we were to take a snapshot of, actually, clear screen. Let's try that again. If we were to take a snapshot, no, come on, man. If we were to take a snapshot of basically that, my goodness. I'm just not going to be, I can't do this. Yikes. I guess I'm just not going to be able to use this. If we were to take a snapshot of this right here, that's our wavelength, give or take. And if we were to watch this wavelength move across in this direction, okay, we would oh my goodness, how to explain this? Because I don't have, this is supposed to be a GIF and it's not moving, which is frustrating, but how to explain it? My goodness. Yeah, it's like you watch for this. Excuse me. You watch for this shape, and what you're doing is you're trying to measure the number of times that this shape moves across a particular point. So if you were to count every time it passed by that line right there I just drew, so I'll draw it again, but in green. Okay, if you were to measure how many times it moves past that, however many times you see that wave, that little snapshot move past that green line per second, or for in a particular amount of time, would be your frequency. Okay, that's frequency. Velocity is how quickly it goes from, say, right here to past that line. Okay, that would be the speed. How long does it take versus how many times it takes? And it's important not to get those two things confused. And hopefully I'll have some. Hopefully you'll get that when we go through a number of different labs and practices. But again, don't get confused between frequency and speed. When we increase the frequency, that doesn't necessarily mean that we have an increase in speed, though it will look like it, because when you have a higher frequency of waves, typically it makes it look like it's moving faster, when in actuality it probably is moving at the same exact speed. Now, to kind of touch on that though real quick. So what would it look like if, let's say if this is the wavelength, so in this picture right here that's on the screen right now, if we started with this wavelength, what would it look like if we increase the frequency? It would just look like this. Okay. That's what it would look like if we were to increase the frequency. Okay. Increase the frequency of the number, so the number of waves that move by, okay, not how quick they're moving by, but just the number of them. Typically, it also reduces the wavelength. Okay, that's frequency. And then again, velocity is just how quickly it moves from, say, from here to here. Okay, how fast does it move? What's the time that it takes? Okay, what's the time it takes to move from this position to this position? Okay, that's velocity. And we'll be calculating that here just shortly. And here are what we use in order to determine just how fast a wave can move. So we can use a formula where its velocity is equal to wavelength divided by time, or the period. Or we can say velocity is equal to the frequency times the wavelength. So now this is just to find, this right here is to find velocity. Now, if we wanted to find, now I know we haven't talked about period and we haven't talked about frequency all that much, or compared them, and we'll compare them here in a second. But if you need to find the wavelength, so if you need to find lambda, here is this is the equation we use here. It's just going to be the velocity times the period. Okay, velocity times time. If we need to find period, it's just going to be period is equal to lambda divided by the velocity, the wavelength divided by the velocity. Okay, so that's what we would do to find using period. And again, we'll get to what period is in here in just a second. And again, this is just to find velocity. Okay, but if we had velocity and we needed to find wavelength, it would be wavelength is equal to lambda is equal to velocity divided by the frequency. Okay. And then if we needed to find the frequency, then it would just be frequency is equal to velocity divided by wavelength. Okay, and that would give us our frequency. Okay, now why should we care about period? Why should we care about frequency? So period, again, is the interval of time between successive occurrences. Really, all that sounds pretty, I guess, complicated. It's really not. Period is just the time it takes for a thing to happen. Okay, how long does it take for a thing to happen? So a question would be, like a period question would be, how many days are in a year? No, sorry, that's the other way around. That's for frequency. It would be like, how many hours are in a day? Okay, so how many hours are in a day? There's 24 hours in a day. That's period. How much time does it take for one thing to occur? In waves, it's like, how many times does a wave oscillate? Meaning, how long does it take for a wave, one wave to be produced, to oscillate? Okay. Frequency is how often something happens. In this case, they say the rate in which vibration occurs that constitutes a wave, either in a material or in an electromagnetic field, usually measured per second. That's a whole lot of gobbledygook, basically just to say how many times something happens, the number of times something happens over time. So a question I would ask you for frequency would be, how many times a day do you look at your phone? So the thing is, how many times do you look at your phone in a day? How many times do you do a thing over time? Another question would be, how many times do you go to school in a week? And for most of us, we would say we go to school 5 times for every 1 week. That's frequency. How often does something happen? How frequently do you do a thing? Period, again, is just how long does it take you to do that one thing? That's the difference between them. And so what they are, and what hopefully you should hear there, is that period and frequency are somewhat related. They're very, very close to one another. And the way that they're close to one another is that they're reciprocals, meaning that they are more or less just mirrored images of one another. So if, let's say we had period, let's say we had period and we needed to know frequency, okay? If we had period but we need to know frequency, frequency is just going to be equal to 1 over t, 1 divided by t. Well, basically the same thing works if we are given frequency but need to know the period. If we need to know the period, it's just going to be 1 divided by the frequency, okay? Because again, they're reciprocals of one another, okay? And remember, reciprocals are just like this. So really, it's t over 1. It's f over 1. So f over 1 is equal to 1 over t. T over 1 is equal to 1 over f. Okay, which makes sense because remember, period, it's just time. We'll say it's time over the thing. So how long does it take to complete the one thing? Frequency is the thing over usually 1 second, we'll say. Okay, we could even just say, keep it easier and just say the thing over time. Okay, the thing over time. Okay, so again, they're just reciprocals. So but you're given the tools here that if you need to find velocity or wavelength, you can either use period or frequency. But for the most part, we're mainly just going to use frequency. Just so you know, we're mainly going to use frequency, but you will see a couple period questions here and there. So anyway, that's pretty much the end of the notes here. So because after this is pretty much just check your understandings. The playing with the slinkies, this is part of this is going to be part of a kind of engagement lesson that we're going to do in one of these days. So this will be talked about in class. Don't worry about this. But anyway, that's pretty much just the notes, guys. So if you still have any questions for me, make sure you ask. If not, I'll see you guys in the next one.